In section 2.5, we'll be finding equations of both quadratic and cubic functions, both algebraically and by using quadratic regressions with our graphing calculator. Our first example is talking about the height of a diver jumping off of a 10-meter springboard, and it's being modeled by this quadratic function, h of t. We're given the graph of h of t, but our job is to find an equation for the function. We know that quadratic equations can be represented in a couple of different ways: standard form, factored form, and vertex form. Since I'm given a graph which clearly shows the vertex, I'm going to use vertex form to try to write an equation of h of t. And I know that vertex form usually looks something like this: a times x minus h squared plus k. Now I also know that with vertex form, this h and k come from the vertex. So I'm going to go ahead and substitute my h and k with the actual values for my vertex here. A times x, and then instead of minus h, I'm going to put minus 1, because that's the x value, my horizontal shift of the vertex. Plus k would be plus 15, that's the y value, that's the vertical shift from my vertex. Now, the tricky thing here is I don't actually know what my a value is off the top of my head. I only have this other point that I can go off of. So I'm going to use this other point, 0, 10, where the x is 0 and the y is 10, to help me find that a value. If I know that x is 0 and y is 10, I can plug those two values into my equation. So my equation, however, has h of t's, and I apologize, these x's should actually be t's instead, because that's what our function has been given us. So h of t is like my y, so instead of h of t, I'm going to put 10 equals a times, instead of t, the t value that I have here for my extra point is 0. 0 minus 1 squared plus 15. Now I can go through and do inverse operations to solve for a. So I'm going to start by cleaning up this right-hand side. I have 10 equals a times, I know that 0 minus 1 is negative 1, and I'm still squaring it, plus 15. Now I know that negative 1 squared is positive 1, so I really have a times positive 1 plus 15. Now I can go and start using my inverse operations to get a by itself. So I can start by subtracting 15. 10 minus 15 is negative 5. I'm going to draw an arrow to show the rest of my work up here. And if you wanted to truly get a by itself, we would divide both sides by 1, which we know isn't really going to change that negative 5 value. So you just figured out that the a value in this vertex form equation is negative 5. We needed that to write our full equation, because remember, we were able to get to this step with our vertex, 1 and 15, but we needed this a value, which we now know is negative 5. So my final equation for h of t is negative 5 times t minus 1 squared plus 15. I can now use this equation to answer the next question. It says, according to your function, how long will it take the diver to reach the water? So I'm looking for this point right here, this x-intercept. If I know that the diver is at the water, the height is 0, meaning I'm going to replace this h of t with 0 and solve for t just by using inverse operations. So, as a review from our last couple of sections, I'm going to start by subtracting 15 from both sides. I'll get negative 15 equals negative 5 times t minus 1 squared. Then I'll divide both sides by negative 5. Negative 15 divided by negative 5 is 3, equals quantity t minus 1 squared. Now that I have the squared thing by itself, I'm going to take my square root, and I get this plus or minus the square root of 3 equals t minus 1. At this point, if you wanted to use your calculator to figure out the square root of 3, since it's not actually a perfect square, it might not be a bad idea. So when I do that, I get that the square root of 3 is about plus or minus 1.732. Okay. Since I have this plus or minus, I'm going to write two separate equations up here. T minus 1 equals positive 1.732, and t minus 1 equals negative 1.732. I'll add 1 on both sides of each equation, and I'll get 2.732, and if I add 1 to that negative, I get t equals negative 0.732. So I was asking, how long will it take the diver to reach the water? This negative time does not make sense. So we would say that the diver reached the water after 2.732 seconds. Okay, so that was a problem in context. Now we can continue to use that same skill of using vertex form of our function and an extra point to find equations for quadratic and cubic functions. So let's actually start with part 2 here. We're going to go a little bit out of order. I know that f is a quadratic function whose vertex is at 411 and it passes through the point 729. So again, just like I did with my previous problem, I'm going to start by knowing what I know about vertex form of a quadratic, and it looks something like this. I know that the vertex of this quadratic is 411, so I'm going to substitute 4 and 11 for h and k. A times x now minus 4. That's really messy. I need to solve for this a value, so that's where I'm going to use my additional point, and I'll say that the y is 29 and the x is 7. So instead of this y in my equation, I'll substitute 29. I do not know what the a value is, that's the whole point, and my x is 7 from that point. Okay, so now it's just a matter of cleaning up this right side and then using inverse operations to solve for a. 29 equals a times 7 minus 4 is 3, and then 3 squared is 9. Now to solve for a, I can subtract 11 from both sides. 29 minus 11 is 18. And then divide both sides by 9, and we get that a equals 2. So what that tells me again is when I write this equation, I knew that the vertex happened at 4, 11, but I now know the a value is 2. So I need to write my final equation, y equals not a. We know that a is 2 times x minus 4 squared plus 11. Now, technically, if we go back and look, we said that f was a quadratic function, so instead of calling this y equals, let's go back and just make that a little bit more proper and call it f of x, and call that our function. Okay. I did that one on purpose first because it follows more of the pattern that we saw in our previous example, but the rest of these, we can really just use the graph to kind of help us figure out what our a value is. So starting with this first graph, I know it's a quadratic, so I know I'm going to be using the form y equals a times x minus h squared plus k. And now I'm just going to go in and fill in everything I know by looking at the graph. I know that my vertex happens here, to the right 3 and up 2. So instead of my h and k, I'm going to put a minus 3 for the horizontal shift and a plus 2 for the vertical shift. To figure out my a value, I'm just going to count from point to point, remembering my pattern from when I graph. Usually, when I graph quadratics, my over and up pattern looks something like this. Over 1, up 1, over 2, up 4, over 3, up 9. So I'm going to see if that holds true here. Okay. First, I notice that this quadratic is reflected, so I know that my a value is going to be negative. Then if I look from my vertex, I went over 1 space and down 1 space. Then again from my vertex, I went over 2 spaces, and to get my next nice point, I went down 1, 2, 3, 4 spaces. So it does follow this pattern. We're just going down instead of up, meaning that our a value is -1. Kind of following that same logic for these next two, the only difference here is that these are cubic functions. So I can still start with my quote vertex form for a cubic function. It looks very similar, we just have to remember to put a cubed for our exponent instead of a squared. And instead of looking at a vertex, we're looking at this middle point of inflection. That point of inflection is shifted to the right 3 spaces and down 4. So for my h and k, I would put a -3 and a -4. And now my job is to figure out the a value. Okay. Again, typically for a cubic function, we think about our over and our up pattern when we graph. When we go over 1 space, we go up and down, I should say, 1 space. When we go over 2 spaces, we go up and down 8 spaces. When we go over 3 spaces, we go up and down 27 spaces. So let's see if that holds true here. When I went over to the right 1 space, I went down 2 spaces. Same thing over here. If I went over to the left, I went up 2 spaces. So what that means is instead of going over 1 and up 1, I actually went over 1 and up 2, which meant I multiplied all of my up and down numbers by 2. So I know that my a value is actually a 2, and specifically in this case, it's a -2 because my cubic function is decreasing as I look from left to right. All right, finally for this last one, again, we see that it's a cubic function. So we're going to start with our quote vertex form of a cubic. We're going to find our point of inflection, this middle point here, which we can see is to the left 3 and up 2. So inside for the h, I'm going to put +3 for left 3 and +2 for the up 2. And then I see that my next very clear, nice point is marked here, meaning I went over 2 spaces and up 1, 2, 3, 4, 5, 6 spaces, which doesn't nicely fit this pattern. And when I look at this over 2 and up 8, it's kind of hard for me to think what number I multiplied this 8 by in order to get my 6. So instead on this problem, I'm going to use the method that I did up here for this cubic, where I know that this point has an x value of -1 and a y value of +8. And I'm going to substitute those two numbers, -1 and +8, for the x and y here, and then use inverse operations to solve for a. So when I do that, instead of y equals, I'm going to say 8 equals a times -1 plus 3 cubed plus 2. If I clean up the right side, -1 plus 3 is 2, and 2 cubed is 8. Okay. Then I will subtract 2 from both sides, get 6 equals a times 8, divide both sides by 8, and I get that a equals 6 over 8, which when reduced gives me 3 over 4. So to finish writing this final equation, I now know that the a value is 3/4.